Hi and welcome to this video from the Year 2 Stats section of the A-Level Maths course. We're looking at the normal distribution, and in previous videos we've been through the basics of where the normal comes from and how to use it to find probabilities. A couple more things to get through, and this one is about how we go about finding values for mu and sigma, the mean and the standard deviation. And what we're going to do is use something called the standardised distribution to be able to find those things. So we're looking at situations where you've got a data set, you've got some information about them, and you want to be able to work out mean and standard deviation. So here we go. If we consider a normal distribution, it's defined by two continuous parameters. We've got mu and we've got sigma. And if you imagine every possible combination of those two values, you'll realise that there's an infinite number of possible normal distributions with those two things. However, what we do have is one particular distribution that is incredibly useful, and that's what we refer to as the standardised normal distribution. And that's the normal distribution with these two parameters. So the mean is 0 and sigma, the standard deviation, is 1, and we call it Z. So Z is the default notation. As soon as you see a Z in the context of the normal, you know you're dealing with that particular distribution. And it's really useful because it gives us one that we know the values about, and it was one where we used to have to spend a lot of time converting from your distribution that you're working with into the standardized one to be able to get values because of the need for massive tables. A lot of that is gone now because of your calculator's ability to do all the calculations for you. But there is a context, that's the one we're talking about today, where we still need that standardized distribution. Key fact is that in order to transform your variable, so you're going to be working with a distribution that's got a value that's x, our continuous random variable x, and to be able to convert x values essentially into z values, we use this simple formula here. So it's x minus mu over sigma. Essentially what that is two graph transformations. It's probably the easiest way of thinking about it. So I'm working with these values over here, and this is a distribution I don't know much about, and I want to convert all these x values and transform them into z values, so it kind of maps to this one here, which I do know something about because that's our go-to setting for normal distributions. So if we think about it as graph transformations, what we've got to do is we've got to do a translation horizontally, which is the shifting by mu units. So what we do is take that curve and just shift it that way. And then essentially what we've got to do is a stretch, a vertical stretch, and we do that by essentially dividing by sigma. And what we've done there is transformed our curve from here, this blue curve, to now this green one, which is on top of Z. That's what's going on. Nobody's ever really going to check too much that you know precisely what's happening. And to be fair, that explanation was a little bit simplified, but hopefully you get the idea. The key thing now is let's have a look at how we can actually make use of it. So here we go. We've got a continuous random variable x that we're told is normally distributed. It's got a mean that we don't know, but we do know that the variance is 1.5. And we've got some information. We know that the probability of getting a value of x less than 10 is 0.6585. So that's the information we're given. We've got to find mu. So what we're going to do is work back from a probability back towards finding a value for our mean. So that's where we're starting off. There's a little sketch of our particular distribution. And we've got the area to the left of 10 is that blue area, that's 0.6585. And what we're going to do is we're going to transform it and find an equivalent value from that standardized distribution. So what we're going to do is we're going to do some number crunching, and we're going to end up with this situation. And what we need to do, we need to find this value for alpha here. This is going to be our equivalent value that's going to help us unlock this problem. So what I'm going to do is I'm going to start over here. And the reason I'm going to start over here is because we know about this one. I've got values for my mean and my variance, so I can put those into a calculator. If we were back over here, we wouldn't be able to proceed with this one because you wouldn't have a value of mu to be able to put into the calculator. That's going to cause the problems. That's the thing we're trying to get around. But we do know it for these. We know all the parameters we need for this one. We've just got to find this one missing thing here. So we need to find a value of alpha such that the probability z is less than alpha is that 0.6585. So that's what we're looking for. So we grab the calculator, we go for the inverse normal function on our calculator, and we find from that we've got a value of alpha is 0.4083. So what we're saying is this 0.4 value in our standardized distribution, we've got everything to the left of this the probability of that happening would be our 0.65. That's the same for this one. So now what we've got to do is use that formula to convert from our standardized value for z back into our distribution that we're looking at for x. So here we go. There's our formula to do the converting. We know that z is this value over here, 0.4083. X, that's our value of 10 that we're given from here. And then we know that this one here is the square root of 1.5. And again, that's one to watch out for, because obviously this thing up here is the variance. It's the standard deviation squared. So we need to make sure we're using root of 1.5. And now what we've got is an equation where we've just got one variable missing. It's mu. We've just got to solve it. So a little bit of rearranging. And there you go. We've got our value of mu. Our mean is 9.5. There we go. So we've used our standardized distribution to be able to just, it's essentially a way of being able to get an equivalent value off a calculator, which we can then convert. Let's go on and have a look at an exam style question. We've got a very chilled out looking otter there. So we've got a colony of sea otters. We know that the masses are normally distributed, mu and standard deviation sigma. And we've got some information. We know 15% of the otters have a mass greater than 35, 5% have a mass less than 25. And let's find a value of mu and sigma. Again, it might be you've spotted what's going on here. We are going to end up with a simultaneous equation because we've got two missing variables and we've got two bits of information. Our first bit of information, this one here. Our second bit of information, 15% less than 35. Second piece of 5% less than 25. Okay, so off we go. Same principle again. That's our distribution for our otters. And that's one we can't work with at the moment because we don't know the key parameters. So we're going to have to go for that one there. We're going to need to find what values for alpha and beta from our two bits of information. So let's start off with alpha. We know that probability z is greater than this value here, is 0.15. Grab the calculator and you end up with alpha being 1.036. Let's do exactly the same now with beta. So we know the probability that z is less than beta is 0.05. And again, putting that one into our calculator using 0 and 1 as our parameters to put into the calculator in the inverse normal calculator function, we end up with a value for beta. So that's those two bits done. Let's now put it all together. Let's link them with our standardization formula. So there's our first one. So for the value for alpha, the equivalent value for x is 35. So we've got that, which we can just do a little bit of rearranging just to get it looking like that. And you can see I'm aiming towards a simultaneous equation here. Same thing with our values for beta and the fact that 5% were less than a mass of 25. Bit of rearranging. And when you do the rearranging, the nice thing is you tend to find that it's the mu's that will cancel out quite simply. Do a bit of subtracting. And there we go. And out pops your value for sigma. And we've got sigma equals 3.73. There's our first value, that's our first parameter that's missing. If sigma is 3.73, that leads us towards mu equal to 31.3 kilograms. And there's the question solved. Right, let's move on to part B. And again, you tend to find that they'll link a normal distribution question with a probability question. Let's just have a look at what's going on with this. We've got a large population of otters. I probably should have put that in the question, but it assumes we've got a large population. We've got 12 being chosen at random. Find the probability at least half of them are heavier than 30 kilograms. So first thing we need to do is find the probability that any individual otter from our population has got a mass greater than 30 kilograms. And because our population is modelled with a normal distribution, let's have a look at that. There we go. It's normal. We've got our found values from the previous part of the question. The mean was 31.3 and the standard deviation 3.73. So let's find the probability that we've got a single otter greater, if we pick one at random, greater than 30 kilograms. So we're going to be doing that calculation, probably x greater than 30. Grab the calculator and you end up with a value of 0.6363. It's at this point that things change a little bit now, because now what we're saying is we've got specifically 12 otters chosen at random, and the probability of any one otter having the criteria we want, which is 30 kilograms, is that probability there. So we've got a fixed number of trials, and we've got the probability of success, 0.6363. So what we're talking about now is a binomial distribution. So we're taking our values that we found from our normal distribution from the whole population, and now we're looking at a fixed number of trials, 12 specific otters, and what's the probability that we're getting at least half of them greater than 30 kilograms. So it transfers into that. So we've got, for our 12 otters, that's our random variable y. It's now a discrete random variable. It's binomial, 12 trials, 0.6363 is our probability of success. So what we've got to do is we've got to prime the probability y equal greater than 6, which you can just put into some calculators, or if you're on a calculator that requires a 1 minus, then do that. Let's say when I wrote this PowerPoint, I was on a calculator that couldn't cope with greater than stuff. So either way, put into your calculator, and there we go. There's your value, there's your probability. So the key thing about this question was how we go from a normal distribution question that kind of segues neatly into a question about the binomial distribution.